So in this part of the lecture, we are going to discuss the first order condition of a convexity of a function f. So let's consider that we have function f, which is a mapping from n-dimensional real vector to a scalar. Then the first order condition of the convexity states that f of y is greater than or equal to f of x plus the gradient of f of x transpose times y minus x for all y belonging to the domain of f. So this is a necessary and sufficient condition for a function to be convex. So any convex function f will satisfy this condition. So this is necessary. And this is also sufficient condition for the convexity. That is, if for a function f, if you prove that the function f satisfies this inequality, then basically you have proven that the function is convex. So this is both a necessary and a sufficient condition for the convexity of a function. So what it means is that, let's discuss the first order Taylor approximation of a function around a point x. So the Taylor approximation, the first order Taylor approximation, so the first order Taylor approximation of any function f at point x plus delta x is equal to f of x plus the gradient of f of x, the gradient of f at x transpose times the delta x. But delta x is some small is a small change in x. So around the point x where delta is small, then the first order Taylor approximation of the function is f of x plus gradient of f of x transpose times delta x plus some constant, right? So since we are considering just the first order approximation, we can just ignore this constant. So what the condition of convexity states that for any y that is in the domain of f, so let's assume that for a sufficiently small delta x, it's a distance between 2 points like y and x, y minus x is equal to delta x. Then what it means is that f of y is equal to f of x plus the gradient of f of x, the gradient of f at x transpose times y minus x, right? So this is the first order Taylor approximation of a function f near the point x, right? So this is a linear approximation of a function f, right? So what this condition for the convexity means is that the first order Taylor approximation of a function at a point x is a global underestimator of the function, right? So let's consider this is our function, this is f of y, and at any point x, if we take the gradient and we linearize the function, we do first order approximation of the function, which is linearize the function at point x. So this tangent, which is a slope, so it passes through x comma fx. So this function represents this line. The slope of this line, if we consider a scalar case, then the slope of this line is given by the derivative of the function d by dx of f at point x. Let's consider this point is some x hat and f of x hat at point fx equal to x hat. So this the slope of this line is given by the derivative of the function, right? So what it means is that the first order Taylor approximation of a function f, if it's a global underestimator over entire domain, so if you select any point x in the domain of f, right? For example, this point. So this is also, as you can see, the first order approximation of the function is always below the function fy. So if the global underestimator, the first order Taylor approximation is a global underestimator of the function f at all the points in the domain of the function f, then the function is convex. So this is what this condition represents. That is, the first order Taylor approximation f of y is greater or equal to f of x plus the gradient of function f at point x transpose times y minus x. So the first order Taylor approximation of the function f is a global underestimator of the function f. So if f satisfies this property for all y in its domain, at every point x in its domain, then the function f is convex. And this is a necessary and a sufficient condition for a function f to be convex. So we can write if the first order Taylor approximation of the function f is always a global underestimator of f, then f is convex. It implies that f is convex. So this is both a necessary and sufficient condition for a function f to be convex. And one of the remarkable property as a result of this condition is that if the gradient of f is 0 at any given point, so let's consider that there is a point x hat at which the gradient of the function f x hat is equal to 0. So that implies for all y in the domain of function f, f satisfies that f of y is greater than or equal to f of x hat plus the gradient of f of x hat times transpose times y minus x. So if this is 0, then this entire term is 0. So this directly implies that f of y is greater or equal to f of x hat for all y in the domain of the function. So what does it mean is that this f at any point at which the gradient of the function f is 0, that point is a global minimum of that function, because for any other y that you can select in the domain of the function, the value of the function will always be greater than or equal to the value of the function at a point x hat. That is, for convex functions, so this as a result of the first order condition of the convexity, if the gradient of f of x is equal to 0 at some point x hat, at some point x equal to x hat belonging to the domain of the function, then for all y in the domain of the function, f of y is greater than or equal to f of x hat, and thus x hat is a global minimum of the function f. And in case of a strictly convex function, the first order condition is for strictly convex functions, we have that f of y is getting equal to f of x plus the gradient of the function f at x transpose times y minus x. Sorry, this is a greater than equal to, this is greater than sign instead of greater than equal to. So any strictly convex function will satisfy this this condition for y not equal to x. So when y equal to x, there is equality. So for any point y not equal to x, a strictly convex function will satisfy this property. And thus, as a result, if the gradient of the function is 0, if this is 0, so there's some x hat at which the gradient of f at x hat is equal to 0, then as a result, what we get is that for all y in the domain of the function, f of y is greater than the f of x. That is, it is the strict, the unique global minimum of the function. X hat. And that is why in the previous lectures, when we discuss linear regression, when we discuss the logistic regression, and even when we considered the L2 norm regularized least square, we obtain the solution, the optimal W that minimizes the loss function by setting the gradient to 0. And it turns out that the loss functions that we have considered so far, that is any norm, the L2 norm loss function over the data set and the L2 norm over the parameter W. So it turns out the L2 norm is a convex function, and that is why the entire objective function was convex. And we use the property of the convex functions that at a point when the gradient is 0 is the global minimizer of the function, and that's why we are able to set the gradient to 0 and obtain the global minimum of the loss function that we minimized in the previous lectures. And in later part of this lecture, we'll prove that any norm is convex, and then the objective of the logistic regression function was also a convex function when we are minimizing the negative of that function, and when we are maximizing, that's a concave function. So this is the necessary and sufficient condition for a function to be convex. And the next part of, in the next part of this lecture, we will provide a proof of the first order condition of the convexity.